Imagine stepping outside on a clear night, looking up at the stars and realizing that everything you see, all the constellations, the glowing band of the Milky Way, the faint smudge of another galaxy millions of years away, is only the glitter on the surface of something much larger and much stranger. It is a bit like discovering that the freckles on someone's skin are only hints of the bones underneath. Except in this case, the freckles are galaxies, and the bones might be a structure so immense that even our most ambitious metaphors need a breather. Astronomers call it the cosmic web, but if we are being honest, the name feels almost modest. This thing spans the universe. It could wrap around your imagination twice and still have enough room to politely ask if you need more space. Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing, but only if you enjoy these calm journeys through the universe. Now, let's begin. The idea that the universe might have a skeleton sounds like something you would overhear in a late-night dorm conversation where someone has had just enough caffeine to believe they cracked the code of existence. But unlike most of those conversations, this one actually has evidence behind it. Observations of galaxies show that they are not sprinkled randomly across the cosmos like cosmic confetti. Instead, they cluster into vast threads and knots, forming a pattern that looks eerily biological. If the universe had an X-ray taken, this is probably the structure that would show up, the framework holding everything in place, guiding its growth, and whispering, "Yes, I am surprisingly organized for something born from a chaotic explosion." It is unsettling in the best possible way. On one hand, it gives the comforting impression that the universe is not a sloppy mess of matter thrown in every direction, like an intergalactic toddler got hold of the physics settings. On the other hand, the scale of it is downright intimidating. These filaments are hundreds of millions of light years long. That is long enough that if you tried to walk it, your great-great-great-grandchildren would still be walking by the time the sun had become a very confused red giant. It is long enough that even light takes so much time getting across that it is basically on a cosmic road trip with no bathroom breaks. But the most compelling part of this cosmic skeleton idea is the way it flips our emotional perspective. Suddenly, galaxies do not feel like lonely islands drifting through emptiness. They are beads strung along invisible lines, part of a skeletal system that connects them across impossible distances. It is like discovering the Milky Way is not floating alone, but clinging to a cosmic spine. If galaxies had feelings, this might be when they look around, realize they are part of an enormous family tree, and have a small existential crisis. There is also something profoundly humbling in realizing that the skeleton of the universe is not made of anything familiar. We are used to bones made of calcium and cells and other earthly materials, but the universe plays by its own rules. Its bones are partly made of dark matter, a mysterious ingredient that refuses to interact with light, electricity, or any of the things our daily lives depend on. Dark matter is the cosmic introvert, shy, invisible, and yet absolutely essential. Without it, galaxies would not stick together. They would fling themselves apart so quickly that star formation would be a brief cosmic fad, not a long-term career choice. Thinking of this invisible stuff shaping the universe is unsettling. In the same way, learning that ghosts might organize your furniture while you sleep is unsettling. Except in this case, the ghosts are not rearranging your couch. They are shaping galaxy clusters, the size of entire supercontinents smashed together. It is hard not to feel a strange awe at that. The universe is not just big, it is structured, sculpted, intricately woven, yet so vast that we only recently realized we were living inside its architecture. And once the idea takes hold, it becomes impossible not to wonder. If the universe has a skeleton, does that mean it is growing? Does it age? Could it change shape over billions of years, the way living organisms do? These are the kinds of questions that transform stargazing from a relaxing hobby into an intellectual roller coaster. One moment you are admiring Orion's belt, and the next you are contemplating whether the cosmos is secretly more alive than you thought. The first chapter of this journey is simply an invitation to stand on the edge of this vast idea and look out over the horizon of what it suggests. The cosmic web is not just a pattern, it is a clue that the universe has an underlying architecture. It is the universe whispering, "You have only seen the surface. Look deeper." And in that whisper, there is something thrilling, an emotional spark that reminds us that every time we think we understand how the cosmos works, it reveals another layer, another structure, another mystery that stretches across space like the bones of a giant we are only beginning to see. Long before astronomers had computers powerful enough to map billions of stars or telescopes sharp enough to peer across cosmic gulfs, they had a simple assumption. Galaxies should be scattered everywhere like spilled sugar on a dark countertop. Neat, simple, and comfortingly random. But the universe, as usual, had other plans. It has never once shown interest in meeting our expectations, and it certainly did not intend to start with something as basic as the distribution of galaxies. So when scientists began collecting the first serious surveys of the sky, they quickly realized something was off. The cosmos was not messy, it was organized. And not organized in a polite, symmetrical way either, more like a giant cosmic knitting project with loops and strands stretching in every direction. The first hints came from painstaking galaxy counts in the mid-20th century, when astronomers spent night after night photographing slices of the sky and cataloging the tiny smudges that turned out to be entire galaxies. It was slow, almost meditative work, the kind that probably made astronomers wonder why they had not chosen hobbies like juggling, pottery, or anything involving a chair with better lumbar support. But as the galaxy maps grew, a strange pattern began emerging. Instead of uniform distribution, galaxies clumped together in elongated shapes, as though they were following invisible lanes that twisted across the heavens. The real turning point arrived with redshift surveys, which allowed astronomers to not only see galaxies, but also measure their distance. Suddenly, the universe went from a flat wallpaper to a three-dimensional landscape, and that is when things got even weirder. When researchers plotted the positions of thousands of galaxies, something appeared that no one expected. Massive chains, arches, and walls of galaxies, so enormous that they stretched across hundreds of millions of light years. Some early astronomers described these shapes as looking like foam bubbles, which is probably the most adorable comparison ever made about structures the size of cosmic megacities. Others said it looked like Swiss cheese, but only if the cheese had been carved by a sculptor with a flair for the dramatic. One particularly famous early discovery was a gigantic arc of galaxies that curved through space like the universe had taken a cosmic ladle and drawn a line across the sky. Astronomers examined the data again and again, wondering if it was a glitch. Did the telescope sneeze? Did someone spill coffee on the printout? But no. The structure was real, and if that was real, then the universe was hiding patterns far larger and more intricate than anyone had imagined. Soon after came the revelation of the first truly enormous walls, immense sheets of galaxies arranged like continents floating in space. These were not just clusters or superclusters, they were structures so large that even naming them required a mix of awe and panic. It was like discovering that the universe had decided to casually drop a Great Wall of China into the cosmos, except this one was billions of times longer and showed no signs of tourist traffic. For the first time, astronomers had to confront the possibility that the universe was not a random scatter, but a web-like system built from interlocking threads. The best part is that these discoveries did not arrive with triumphant music or dramatic lighting. They came from people hunched over computer terminals, comparing graphs and squinting at plots. There is something wonderfully humble about the moment someone realized, wait, these galaxies are lining up, followed immediately by the cosmic equivalent of discovering your backyard garden is actually growing in the shape of a giant, spiraling dragon. As technology advanced, surveys expanded from thousands of galaxies to millions, each new dataset reinforcing the same conclusion. Galaxies are social creatures. They do not roam the universe alone like lone cowboys drifting through the desert. They gather, cluster, cling, and stretch into colossal filaments that curve like the threads of an unfinished cosmic sweater. If the universe had a hobby, apparently it chose knitting. Although given the scale of these structures, it is knitting on such a level that yarn companies everywhere should feel personally threatened. The deeper astronomers looked, the more elaborate these patterns became. Galaxies did not just form straight lines, they braided, they forked, they merged into nodes where dozens of filaments met, forming knots so dense they gave rise to massive clusters. And between these threads were huge yawning regions with almost nothing inside, voids so empty they made vacuum cleaners look inefficient. What startled scientists most was not just the existence of these shapes, but the consistency of them. No matter which region of the sky they surveyed, the universe displayed the same sprawling, interconnected architecture. Of course, this realization created more questions than answers, which is scientifically acceptable but emotionally rude. Why did galaxies follow these structures? What forces guided them? Was there a blueprint, a cosmic architect, a manual titled How to Arrange Your Universe in 14 Easy Steps? While the ultimate explanations would take years to uncover, those early observations set the stage for a seismic shift in how humanity viewed the cosmos. For the first time, people understood that the universe was not a scattered sea of lonely galaxies drifting aimlessly through darkness. It was a cohesive landscape shaped by vast, unseen influences, weaving galaxies into strands that stretched farther than imagination could comfortably follow. And all of it began with those early moments, those tiny points on a page gradually forming lines that revealed the universe had been quietly threading a cosmic tapestry all along. If you could step outside the universe and look at it from a vantage point impossibly far away, farther than any telescope could dream of reaching, you would not see a smooth ocean of stars spread evenly across the dark. Instead, you would see something far stranger and far more intricate. The universe would look like a colossal, three-dimensional network sprawling in every direction, shaped by gravity, time, and strange ingredients we can barely describe. This immense structure is what astronomers call the cosmic web. It is not a web in the sense of silk or spiders, although the comparison is tempting, because its pattern does resemble threads stretching across unimaginable distances. It is a web made of galaxies, dark matter, and vast empty regions, arranged in a design so grand that planets, stars, and even entire galaxies become mere decorative beads placed along invisible lines. To understand this structure, imagine being inside a room filled with fog. You wave your hand and you notice thicker patches and thinner patches. Now imagine that instead of fog, you are surrounded by billions of galaxies, and the thicker patches are where galaxies cluster into vast filaments, while the thinner patches are where they thin out into desert-like voids. The cosmic web is a universe-scale version of that idea, except the fog is distributed across distances so large that even light, which never loafs around on the job, takes hundreds of millions of years to cross some of its features. The web is made of filaments, which are long, thread-like structures containing chains of galaxies, like glowing beads arranged along an invisible spine. These filaments are not gentle wisps. They are enormous, rigid highways of matter stretching across space. Picture a cosmic string so long that it could circle the Milky Way not once, but thousands of times, and you still would not reach its end. These filaments often intersect at dense regions called nodes, where many threads meet, forming heavily populated zones filled with galaxy clusters. From above, it would look like the intersection of grand cosmic boulevards, where the traffic is made of swirling star systems instead of cars. Between these filaments lie the voids, vast, nearly empty expanses where almost nothing exists. These voids are so large that calling them empty feels like an understatement. They are the universe's equivalent of shouting into a canyon and receiving no echo because even the canyon is too overwhelmed by the silence. A single void might span hundreds of millions of light years, And if you place the entire Milky Way inside one, it would feel like dropping a grain of sand into a warehouse the size of a continent. The contrast between the crowded filaments and the barren voids gives the cosmic web its distinctive sponge-like pattern. If a cosmic baker ever carved a loaf of bread from starlight and carved enormous holes into it, this is probably what it would resemble. One of the most astonishing features of the cosmic web is its complexity. It is not a simple grid or a tidy arrangement. The filaments curve, twist, split, and rejoin like rivers wandering across a continent. Certain stretches are thick and bustling with activity, packed with galaxies growing, colliding, and forming stars. Other stretches thin out into quiet strands where galaxies trickle like the last drops of water in a drying stream. It is a dynamic, evolving network, constantly shifting as gravity slowly pulls matter into new shapes over billions of years. Because the cosmic web is so enormous, our understanding of it comes from stitching together countless observations and running simulations that attempt to recreate its structure. When scientists look at slices of the universe, they often see the filaments glowing faintly with galaxies that trace the hidden shape underneath. The galaxies themselves act like lanterns hanging along invisible beams. You do not see the beams directly, but their presence becomes clear from the way the lanterns gather along their length. These patterns are not accidental. They reveal an underlying architecture guiding where galaxies choose to form, where they move, and how they grow. The cosmic web is not made only of visible matter. Much of its mass comes from material we cannot see at all, something invisible, silent, and stubbornly uncooperative with all forms of light. This invisible material stretches through space like the dark wooden frame of a house whose walls are made of starlight. The galaxies that appear bright and dramatic are like the paint. The invisible structure beneath them carries most of the weight. Even though we cannot see this hidden mass directly, its gravitational influence pulls galaxies into place along the filaments, shaping the entire cosmic landscape. As massive as the cosmic web is, it also has a surprising delicacy. Filaments can be extremely thin compared to their length, almost like cosmic tendrils drifting through the darkness. Some are thick and robust, filled with countless galaxies, while others are so faint that they barely register on our deepest observations. They form a hierarchy, smaller filaments feeding into larger ones, which in turn link to enormous skeleton-like structures holding galaxy clusters in place. One of the most arresting realizations about the cosmic web is that it sets the stage for everything happening in the universe. The birth of stars, the formation of galaxies, and the growth of clusters all occur along this intricate network. Without it, matter might have been scattered too thinly for galaxies to form at all. Instead, the web gathered matter into the right places, encouraging structure to emerge. Seen as a whole, the cosmic web is the universe's grand blueprint, a sprawling system of filaments and voids that shapes everything from the smallest star systems to the vast continents of galaxies drifting across the cosmos. It is an immense, delicate, and breathtaking design, one that reveals the universe not as a random scattering of stars, but as a carefully woven tapestry stretching from horizon to horizon. If you could rewind the universe all the way back to its earliest moments, you would not see the elegant, interconnected cosmic web we know today. You would see something far more unruly, an energetic fog of particles that had absolutely no intention of forming anything neat or impressive. In those early ages, matter behaved like guests at a wild party who had shown up without a plan, without boundaries, and without any clear idea of where they were supposed to stand. It was chaos, hot and loud, and expanding in every direction, yet hidden inside this chaos was a quiet force already plotting its long-term masterpiece. Gravity does not rush. Gravity waits, nudges, tugs, and insists. It is the patient sculptor of the cosmos, and across billions of years, it turned that early clutter into structures so vast and organized they make human city planning look like scribbles on a napkin. Gravity began its work with subtlety. It started with the tiniest differences in the density of matter, minuscule regions that were ever so slightly thicker or thinner than their surroundings. These differences were microscopic compared to the scale of the universe, and so small that no observer could have picked them out if they had been floating nearby. But gravity has a talent for turning whispers into shouts. Even the smallest concentration of matter exerts a pull on everything around it, and over unfathomable stretches of time, these gentle pulls added up. The thicker regions pulled in more matter, which made them even thicker, which allowed them to pull in even more. It was the ultimate winner-takes-all situation, played out on the largest stage imaginable. As time stretched out, gravity's influence grew stronger and more defined. The initially random patterns began to buckle and shift under its persistent tugging. Matter streamed toward regions where gravity had gained the upper hand, forming thin rivers that slowly carved paths through the expanding universe. These rivers widened with time, gathering star-forming material, smaller clumps of matter, and eventually entire young galaxies. In the early universe, these pathways would have looked like shallow grooves forming in a spreading sea. But gravity had only just begun its slow-motion choreography. Billions of years passed, and the grooves deepened into channels. These channels branched like roots, merged like tributaries, and gradually formed the immense frameworks we now recognize as filaments. Gravity had managed something remarkable. It coaxed matter, which began as a nearly uniform haze, into long, interconnected threads. And unlike human artists, gravity did not need tools, nor did it ever step back from its creation to reconsider the symmetry. It simply followed the laws of the cosmos, tugging matter into place with relentless precision. One of gravity's most impressive feats was orchestrating the region between filaments, the vast expanses that would eventually become enormous cosmic voids. As matter streamed toward the filaments, the areas between them thinned out, leaving behind startling emptiness. It was as if gravity had decided not only to sculpt the matter-rich regions, but also to hollow out grand caverns in between, enhancing the contrast and giving the universe its distinctive sponge-like pattern. The voids did not form because something swept matter outward. They emerged because gravity was so focused on gathering everything into the filaments that the surrounding regions were left dramatically understocked. Inside the forming filaments, gravity continued to refine the structure. Galaxies grew heavier and more complex through repeated mergers, each one guided by gravity's careful steering. Smaller galaxies spiraled toward larger ones, drawn in by the gravitational wells that deepened with every new addition. These interactions were not polite, gentle meetings. They were full-speed cosmic collisions, each one reorganizing stars, gas, and dust into new shapes. Gravity oversaw all of it with calm inevitability. It never rushed, never hesitated, never changed its mind. It simply followed its script, allowing chaos to collapse into coherence. Over more billions of years, the intersections between filaments grew into dense hubs. These hubs became the bustling centers of the cosmic web, where galaxies gathered in enormous clusters, bound together by gravity that had grown immensely strong. These regions acted like anchors, holding the entire structure together. Around them, filaments stretched outward in every direction, forming enormous scaffold-like designs. If someone were to view it from afar, they might suspect that gravity had been working from a blueprint, even though the blueprint was nothing more than the natural laws written into the fabric of space. Even today, gravity's sculpting is not finished. Matter continues to drift along the filaments toward the dense intersections, almost like cosmic commuters traveling toward the busiest parts of a city. The filaments themselves subtly shift as more matter flows through them, growing thicker in some regions and thinning in others. Gravity is still pulling, still shaping, still refining a structure that began as randomness and transformed into breathtaking organization. What makes gravity's achievement so astonishing is its simplicity. It is not a force that plans ahead or calculates complexity. It works everywhere at all times, tugging matter closer with absolute impartiality. Yet from this single, unchanging rule emerged a universe with structure so intricate that no human engineer could replicate it. Gravity took chaos and gave it form, not through speed or force, but through patience on a scale that only the cosmos can afford. And in doing so, it created the grand architecture that everything in the universe now calls home. Picture a universe where most of the important work is being done by someone you cannot see, cannot hear, and cannot poke with any known instrument. This someone never complains, never takes a vacation, and never receives any credit on official paperwork. That someone is dark matter, the invisible backbone of cosmic structure, the quiet supervisor, making sure galaxies do not fling themselves into the void like unsupervised toddlers discovering sugar for the first time. If the cosmic web needed a full-time crossing guard, dark matter applied for the position before galaxies even existed and has been on duty ever since. To understand why dark matter is so essential, imagine a galaxy as a spinning carousel. The stars whirl around the center at incredible speeds, and logic says that if only the visible matter were present, Many of those stars should be slingshot into space like runaway sparks, but they do not. They stay in orbit, behaving as though an enormous amount of unseen mass is holding everything together. Astronomers first picked up on this strange behavior when they noticed galaxies moving in ways that made no sense unless there was extra mass hiding somewhere. That mass refused to emit light, reflect light, or otherwise interact in ways normal matter does. It was the universe's first hint that something invisible and powerful was shaping everything from behind the scenes. Dark matter acts like a huge, invisible scaffolding that forms the skeleton of the cosmic web. Before galaxies even had the chance to ignite their first stars, dark matter had already begun gathering into immense clumps. These clumps were like cosmic neighborhoods waiting for visible matter to move in. Gravity pulled the ordinary matter, hydrogen, helium, and all the ingredients destined to become stars, into these dark matter wells. It was as if dark matter built the apartment complex, and visible matter rushed in to fill the rooms, unaware they were relying on a landlord they would never meet. This gathering process was not gentle. Dark matter formed enormous halos, vast spheres of invisible mass that wrapped themselves around forming galaxies. Within these halos, matter settled into rotating disks, star clusters, and spiraling arms. Every structure that came into being did so, while dark matter quietly kept everything anchored. Without dark matter, galaxies would wander off like distracted shoppers in a supermarket aisle, bumping into each other or drifting too far apart for gravity to maintain any meaningful structure. Instead, they move along controlled paths, nudged and guided by the gravitational pull of these unseen halos. Think of dark matter as that overworked crossing guard on a busy road. The galaxies are pedestrians with questionable attention spans, trying to move in all directions at once. Dark matter steps in, raises its invisible hand, and says, "Let us try to stay in line, please." It does not shout, does not wear a reflective vest, and does not enforce its rules with flashing lights. It simply exerts gravity from behind the curtain, gently but firmly keeping galaxies where they need to be. One of the strangest things about dark matter is how completely indifferent it is to everything except gravity. Ordinary matter gets tangled up in all sorts of interactions. It collides, heats up, cools down, radiates light, sticks together, and changes state depending on temperature. Dark matter does none of that. You could have a crowd of dark matter particles pass through a planet without leaving so much as a fingerprint. They do not bump into each other. They do not group up the way normal matter does, and they certainly do not glow. Yet they carry far more mass than all visible stars combined. It is a cosmic paradox. The stuff we cannot see outweighs the stuff we can see by a large margin, because dark matter does not interact with light. Its presence is revealed only through the motions of galaxies and through the way it bends light from distant objects. This bending effect, called gravitational lensing without using shorthand, stretches and warps the image of galaxies far behind these dark matter lumps. Imagine walking past a funhouse mirror shaped entirely by invisible hands. The reflection changes not because the glass is curved, but because an unseen force is distorting the space between you and the mirror. That is what dark matter does on a scale so massive that it reshapes entire clusters of galaxies. In the context of the cosmic web, dark matter is not content to just hover around individual galaxies. It gathers along the filaments themselves, creating long corridors of gravitational influence that guide galaxies into position like marbles rolling along invisible grooves. These grooves stretch across distances so large they make the word gigantic pack its bags and admit defeat. As galaxies travel along these pathways, dark matter ensures they follow predictable routes instead of drifting into the vast desert-like voids where almost nothing happens. Even the empty spaces owe their emptiness to dark matter. When dark matter formed filaments and nodes, it left behind regions with very little mass, which became the deep, silent voids between the threads. Dark matter did not create emptiness deliberately. It simply concentrated in other places, and gravity followed. What remained was quieter than quiet, vast expanses where the occasional lonely galaxy seems to float like a single dust mote in a cathedral. The most astonishing part of all this is that dark matter does its job without ever revealing its identity. Scientists have spent decades trying to understand what dark matter is made of, how it forms, and why it interacts so reluctantly with ordinary matter. Yet no direct detection has ever been confirmed. Dark matter is like the universe's most committed employee, always present, always working, never speaking up, and perfectly content to let the galaxies shine in the spotlight. In many ways, the cosmic web owes its existence to this silent architect. Dark matter shaped the original scaffolding, pulled galaxies into place, and continues to guide the evolution of the universe with its unwavering gravitational grip. Without it, the cosmic web would be a tangle of loose threads. With it, the universe gains a sense of structure, stability, and harmony, crafted not through visibility or brilliance, but through the quiet, persistent pull of something that refuses to be seen. Long before galaxies spun themselves into graceful spirals, and long before dark matter gathered into vast invisible frameworks, the universe was a hot, dense ocean of particles packed together so tightly that light itself could not move freely. It was a glowing fog where photons bounced around like panicked bees, unable to travel in straight lines for even a heartbeat. If you had tried to look through that early universe, it would have been like staring into a pot of boiling soup. Nothing had settled yet. Nothing had separated into familiar forms, and the cosmic web was still billions of years from becoming the intricate structure we know today. But hidden inside that turbulent fog were tiny variations, infinitesimal differences that would become the first sketches of the universe's future skeleton. When the universe finally expanded and cooled enough for atoms to form, something miraculous happened. Light broke free. Photons no longer crashed into particles every trillionth of a second. Instead, they streamed outward across space, carrying with them a frozen snapshot of what the universe looked like in that era. That ancient light still exists today, stretched into gentle microwaves, by billions of years of cosmic expansion. We call it the cosmic microwave background, and it is the oldest picture of the universe ever taken. It is a baby photo, taken long before galaxies, before stars, before even the faintest hint of the cosmic scaffolding that would one day support them. At first glance, the cosmic microwave background looks deceptively simple, a nearly uniform glow spread across the entire sky. But once scientists started studying it with sensitive instruments, they found subtle variations in temperature and density, small enough to be measured in differences less than a single part in 100,000. These tiny fluctuations were the earliest whispers of structure. They marked spots where matter was ever so slightly thicker or thinner than its surroundings, forming a pattern that stretched across the entire young universe. If the cosmos were a blank sheet of paper, these were the first faint pencil marks outlining where its great structures would eventually rise. The remarkable thing about these fluctuations is how gentle they were. Nothing dramatic, nothing loud or obvious, just quiet imbalances created by the chaotic ebb and flow of particles in the early universe. Yet those minute variations would eventually be magnified by trillions upon trillions of years of gravitational pulling. Areas with slightly more matter would become the seeds of the great filaments and clusters. Areas with slightly less would become the deep voids that now span astonishing distances. The cosmic microwave background was not just a relic of the early universe. It was a blueprint written in the softest possible ink. When scientists first mapped this ancient light in detail, the results were astonishing. They saw patches of slightly warmer and cooler regions forming a mottled pattern across the sky. A pattern that seemed almost random and yet held deep significance. Each of those tiny warm and cool spots represented the delicate beginnings of the cosmic skeleton. Even though nothing resembling a filament or galaxy existed at the time, the differences in density would later guide matter into the same patterns we see today. It was as though the universe had sketched the outline of its bones first, letting gravity come along billions of years later to add the muscle and flesh. Some of the earliest detailed measurements came from satellites that scanned the entire sky with incredible precision. They produced maps that looked like speckled globes dotted with tiny variations, each one a clue to how matter was distributed in the universe's first moments. These maps allowed scientists to rewind the cosmic clock and understand how regions of slightly higher density could later collapse into enormous structures. The cosmic microwave background became a Rosetta Stone for the universe's formation, revealing the earliest signs of the same vast patterns that would later stretch across billions of light years. One of the most surprising discoveries hidden in this ancient glow was the scale of the fluctuations. They were spread across the sky in a way that suggested the universe had undergone a brief but explosive growth spurt in its earliest instance. This rapid expansion smoothed out the cosmos, but not perfectly, like a baker flattening dough with just enough pressure to remove the biggest bumps while leaving tiny variations behind. Those leftover ripples became the foundation upon which the cosmic web eventually assembled itself. The cosmic microwave background also showed that the early universe was remarkably consistent, with no privileged region or direction. Everywhere you looked, the same mottled pattern appeared. This uniformity is what allowed the web to grow symmetrically across space, giving rise to filaments and voids in every direction. It meant that no matter where you traveled in the universe, you would eventually find the same repeating architecture, shaped from the same primordial ingredients. What makes the cosmic microwave background so profound is that it lets humanity glimpse the earliest thoughts of the universe. It shows us the moment when structure first became possible, when the cosmos quietly decided where its future bridges, walls, and intersections would form. The image encoded in those microwaves is not a map of what the universe was, but a promise of what it would become. Billions of years later, when we observe the cosmic web stretching across space, we are witnessing the fulfillment of those early patterns. Every massive cluster, every spindly filament, and every yawning void grew from the initial differences etched into the cosmic microwave background. The universe did not begin with chaos blindly forming order. It began with a gentle pattern, barely noticeable, slowly amplified by time. And from that pattern, the cosmic web emerged, just as the earliest sketch foretold. Imagine taking the Milky Way, our grand, spiral-shaped cosmic home filled with hundreds of billions of stars, and placing it gently on a table next to the universe's largest structures. Next to these giants, our galaxy would look like a tiny decorative coaster, the sort you lose under a stack of mail. These colossal formations are not merely big. They stretch the very definition of size into something almost comedic. If the cosmic web were a movie, the Milky Way would not even make it onto the main cast list. It would be the background extra strolling across the screen, oblivious to the fact that titanic structures are towering just off camera. Let us begin our cinematic tour by drifting toward one of the most massive characters in this great cosmic ensemble, the superclusters. These are not single clusters of galaxies. They are collections of many clusters, bound loosely together by the gentle pull of gravity over unfathomable distances. Moving through a supercluster is like passing between mountain ranges made of entire galaxy families. Stars sparkle across these regions, like campfires scattered on vast cosmic plains, except the plains extend for hundreds of millions of light years. On human scales, it is so large that even imagination has to lace up its hiking boots. One of the most striking examples is the structure our own galaxy belongs to, a huge region known as a supercluster of interwoven galaxy groups. In this region, our Milky Way drifts like a resident of a minor suburb on the edge of a sprawling cosmic metropolis. From afar, these superclusters appear as glowing knots of filaments tied together, each one a bustling intersection where gravitational highways converge. Traveling through one would be like navigating through a city so enormous that each building is itself a galaxy containing countless suns. Yet even these titanic collections look modest compared to the truly immense walls that stretch across the cosmic web. These walls of galaxies and dark matter form enormous sheets, dense enough to hold countless clusters, yet thin enough in comparison to be described as cosmic membranes. If superclusters are mountain ranges, these walls are the continents, vast, interconnected landmasses floating in the ocean of space. Picture drifting along an edge of one such wall. Ahead lies an enormous sweep of galaxies arranged in a plane so broad it takes your breath away. It is like hovering beside a cosmic cliff face, except instead of stone, it is built from swirling star systems, each one itself a luminous island of billions of suns. The sheer scale of it presses on your imagination. You could travel along its length for billions of years and never see it end, watching as galaxies glow and dim like lights in a sprawling nighttime city. These walls often form boundaries between immense voids, regions of near emptiness where galaxies grow sparse and silence deepens into something almost spooky. From inside the void, looking toward a wall is like seeing the universe's skyline stretching across the cosmic horizon. The wall glows faintly with starlight, curving in a way that hints at its colossal structure. If sound could travel across such distances, the wall might hum like a magnificent cosmic organ. But space is quiet, and so its grandeur is expressed only through light and gravity. Beyond the walls lie some of the largest structures ever discovered. Immense arcs and formations that bend across the cosmos with a subtlety that only becomes clear when viewed from great distances. These arcs are not tight curves like rainbows. They are sweeping bends so vast that they defy intuitive understanding. They are evidence that the cosmic web does not simply stretch outward. It flows, twists, and folds in ways that make the universe feel alive, moving ever so slowly on a timescale too immense for human senses. Then there are the supercluster complexes that link multiple massive structures into something bigger still. These complexes form labyrinths of filaments and nodes, so intertwined that they resemble the vascular system of a being too large to exist. They are not single structures with clear borders. They are cosmic neighborhoods stitched together by gravity's persistent pulling. Each part influences the next, creating patterns of motion that extend far beyond any individual cluster. If the cosmic web had weather patterns, this is where they would form, mass drifting, clustering, sliding along the unseen scaffolding. Standing back, if one could stand back, the cosmic web becomes an enormous tapestry woven from these immense structures. The walls, the arcs, the superclusters, each is a thread in a design so grand that it dwarfs the concepts of size and distance. The interconnected filaments stretch between these colossal formations like glowing suspension cables, giving the universe a sense of tension and balance, as though everything is part of a vast architectural plan. And in the middle of all this immensity sits the Milky Way, gently rotating, unaware of its position in this staggering network. It feels almost comical. Here we are drifting inside a galaxy that is itself enormous beyond comprehension, and yet we inhabit a space that, when viewed against the universe's grandest structures, feels quaint, cozy even. the galactic equivalent of a studio apartment tucked inside a skyscraper the size of a continent. But there is beauty in that humility, babe. These enormous structures remind us that the universe thrives on scale, on layers of enormity built upon more enormity. The cosmic web is not a collection of isolated giants. It is a continuous, harmonious structure where every part influences the next. From the smallest galaxies to the grandest walls, everything plays a role in shaping the cosmos. And while our home galaxy may be tiny in the face of these titans, it is still a vital thread in the universe's greatest masterpiece, the cosmic web stretching across the vastness of existence. If the filaments of the cosmic web are the bustling highways of the universe, then the voids are the empty deserts stretching between them, stark, silent, and so spacious that even the word vast starts clearing its throat in embarrassment. These voids are not just empty by accident. They are regions where the universe has embraced solitude on a scale so ambitious that it feels almost theatrical. If galaxies had social preferences, the voids would be the spots they studiously avoided, like the cosmic equivalent of a restaurant nobody ever recommends, but everyone knows is there. Stepping into a void is like stepping into a dream where distance has lost all meaning. The nearest galaxy might be hundreds of millions of light years away, a faint smudge drifting in the far-off dark. Imagine standing in the middle of an open field so huge that even turning in a complete circle gives you no landmark, no tree, no hill, not so much as a stray pebble to anchor your perception. Now expand that feeling until the emptiness surrounds you for a distance so great that light itself has to pack a cosmic lunch just to travel across it. That is what a void feels like. These voids formed naturally as the cosmic web took shape. When gravity pulled matter into filaments and nodes, the regions in between were left behind, not deliberately emptied, but simply bypassed. Matter flowed like water toward the densest regions, leaving the voids as the drained basins between the currents. The result was not a sprinkle of emptiness, but entire realms where the density of matter is so low that if you placed a single galaxy inside, it would feel like a lonely traveler stranded at the edge of existence. What makes these voids so astonishing is not just their emptiness, but their diversity. Some voids are relatively small, dwarfing only a few galaxy clusters. Others are so enormous that they could comfortably swallow entire superclusters and still complain about feeling cramped. The largest known voids stretch so far that they function as cosmic skyscrapers made entirely of nothing. It is a strange sort of majesty, beauty defined not by presence, but by absence. As you move deeper into a typical void, the universe grows quieter, not in a literal sense, since space has no sound, but in the sense of activity. Galaxies in these regions tend to be isolated wanderers, evolving differently from their sociable cousins out in the filaments. They form stars more slowly, grow differently, and often take on shapes that make astronomers raise an eyebrow. It is as if the galaxies in the voids are independent filmmakers, making strange experimental choices simply because no nearby galaxies are around to judge them. Despite their emptiness, voids are not completely deserted. They often contain faint threads of matter, whispers of the cosmic web that never grew thick enough to become proper filaments. These threads are like ghostly spider silk stretching through the darkness, so faint that only the most sensitive instruments can detect them. They are reminders that even the emptiest places still carry the faint echoes of the universe's larger design. On rare occasions, astronomers spot unusual structures inside voids, solitary galaxies or small groups that seem to cling stubbornly to their lonely existence. These galaxies are peculiar. Some are surprisingly isolated, as though they got lost on the way to a cosmic gathering. Others have strange characteristics, like forming stars at odd rates or showing unusual patterns in their internal motion. Living inside a void gives a galaxy a different set of pressures and opportunities. Without close neighbors tugging on them or colliding with them, these galaxies evolve almost like creatures on an isolated island, free from outside interference, but also deprived of the energy exchanges that shape busier galactic environments. Perhaps the most mind-bending quality of the voids is their role in the universe's overall balance. They provide contrast, dark, silent arenas that amplify the visibility of the crowded, luminous filaments. Without voids, the cosmic web would not look like a web at all. The structure would be smoother, more evenly spread, lacking the dramatic interplay of presence and absence that defines its appearance. The voids sharpen the architecture of the universe, making the filaments shine more brightly by surrounding them with unblemished emptiness. Because voids are so empty, they behave differently from denser regions of space. As the universe expands, voids tend to stretch faster than the regions with more matter. It is as though the emptiness itself is eager to grow, pulling away from the filaments and enlarging their boundaries. Over billions of years, this expansion has turned small pockets of low density into enormous realms of near nothingness. Voids are the natural expression of the universe's growing pains, expanding alongside the cosmos and giving it room to breathe. For all their drama, voids seldom attract the popular imagination. Galaxies and clusters get the attention with their bright stars and dynamic interaction. But the voids deserve admiration for a different reason. They illustrate the universe's willingness to embrace silence and stillness just as enthusiastically as it embraces creation and motion. They are the cosmic counterpart to open ocean, snow-covered plains, and deep caves, places where the absence of noise becomes its own kind of presence. In the grand tapestry of the cosmic web, the voids are its negative space, its quiet stretches, its pauses between cosmic sentences. They are the spaces where the universe takes a breath before continuing its story. And although they are defined by emptiness, they are some of the most important regions in the cosmos, shaping the overall pattern and giving the universe its striking, sprawling geometry. These voids, vast and understated, remind us that in the universe, even nothingness has a role to play, and sometimes nothingness plays it to perfection. If the universe had a time-lapse button, scientists would have pushed it centuries ago. Watching galaxies form and merge, watching filaments stretch across space, watching the cosmic skeleton assemble itself piece by piece. It would be the most ambitious documentary ever recorded. Sadly, the universe is not equipped with a fast-forward feature, so scientists did the next best thing. They built one. Using enormous computer simulations, they recreated the cosmos inside digital worlds, letting time zip by at impossible speed and revealing how the universe knitted its grand structure together. These simulations are not mere visualizations. They are full-fledged laboratories where researchers test the laws of physics on a cosmic scale. Watching entire universes evolve in a fraction of the time it took for the real one to grow. Creating one of these simulations begins with something surprisingly humble, a sea of tiny points representing bits of matter spread across a vast virtual space. At first glance, the scene looks unremarkable, just a cloud of dots floating in emptiness, but each dot carries the weight of physical laws, programmed to interact through the same gravitational rules that govern the real cosmos. When the simulation begins, the dots start to move, not randomly, but in response to tiny differences left over from the earliest conditions fed into the program. The digital universe begins as a subtle, uneven mist, and almost immediately the seeds of structure begin to form. As the simulated clock ticks forward, the dots start drifting toward one another, gathering into thin threads, just as matter did in the real universe. Filaments begin to take shape, weaving themselves across the simulation like cracks forming in ice. Given more time, the clusters at their intersections grow heavier and brighter, becoming digital stand-ins for the great hubs of galaxies we see today. Watching one of these simulations unfold is like watching the universe sketch its skeleton with invisible chalk. First a faint outline, then more confident strokes, and finally the fully developed framework spanning the entire simulated volume. These simulations are breathtaking not only for their beauty, but for their scale. Some of the largest ones model regions of space so enormous that billions of particles are required just to represent the underlying dark matter. Each particle is not a literal star or atom, but a stand-in for a vast amount of mass, making the simulation both manageable and meaningful. Each particle interacts with every other through gravitational forces, and the computer must calculate these interactions repeatedly as the universe grows. It is a computational ballet performed at speeds no human could ever follow. Part of the magic lies in how fast everything happens. In reality, cosmic structures take billions of years to evolve. In a simulation, the universe ages right before your eyes. Dense regions collapse, clusters form, filaments stretch, and the cosmic web emerges in mere minutes or hours, depending on the computing power. This fast-forward evolution offers scientists something impossible in real life: the ability to observe the birth, adolescence, and maturity of the universe in a single, continuous narrative. But simulations do more than show what the universe looks like. They test ideas. Scientists can tweak assumptions, changing how matter behaves, adjusting the density of certain components, or altering the initial conditions, and see how the virtual universe responds. If the final structure looks like the real cosmic web, the assumptions were likely correct. If the simulation produces something wildly different, then something in the cosmic recipe needs adjusting. It is like baking the universe over and over, testing different proportions until the structure rises just the way nature intended. One of the most enlightening aspects of these simulations is how closely they reveal the relationship between visible matter and the hidden scaffolding underneath. The simulated dark matter forms the backbone of the web, creating long corridors of gravitational influence, and the digital galaxies follow these corridors perfectly. The visible structures in the simulation cling to the dark matter filaments, like beads sliding along invisible wires, showing just how dependent galaxies are on the unseen forces that shape their paths. Without these simulations, we would be guessing at how the skeleton forms. With them, we get to watch the bones knit together in real time. Of course, simulations also come with challenges. They must balance detail with size, because modeling the entire universe with perfect resolution is far beyond even the most powerful supercomputers. Some simulations focus on small regions with incredible detail, tracking the formation of individual galaxies. Others emphasize enormous volumes, sacrificing fine texture to capture the web as a whole. Together, these approaches help scientists build a layered understanding of cosmic evolution, like zooming in and out of a map to appreciate both the streets and the continents. Despite these limitations, the simulations remain astonishingly accurate. When their results are compared to real surveys of the sky, the match is so close that it feels like looking at two versions of the same artwork, one created by nature, the other painted by code. The digital filaments stretch in the same patterns, voids blossom in the same empty regions, and clusters form in the same dense knots. It is an elegant confirmation that our understanding of cosmic physics is on the right track. Watching a simulation of the cosmic web evolve is like witnessing the universe grow its skeleton and fast forward. The delicate outlines sharpen into a sprawling network, the empty spaces widen into vast chambers, and the filaments tighten into luminous corridors of structure. It is a grand, sweeping performance staged inside a machine, a reminder that even when we cannot travel across time or space, we can still recreate the universe's most magnificent architecture in the quiet glow of a computer screen. If galaxies were left to drift freely through space, their evolution would be a far more chaotic and lonely affair. They would spin and wander without guidance, meeting other galaxies only by accident, forming stars whenever conditions happen to allow it, like campers lighting fires wherever the dry wood happened to pile up. But galaxies are not wandering aimlessly. They live inside a colossal transportation network, the cosmic web, that shapes their fates from the moment they first spark into existence. The web is not just a backdrop. It is an active participant, guiding galaxies along its filaments and influencing everything from their star-making habits to their grand, slow-motion migrations across the universe. To understand how powerful this influence is, imagine a galaxy forming inside a filament. It is like being born beside a highway instead of in the middle of wilderness. Along this cosmic road, raw material constantly flows inward, streaming hydrogen, drifting dust, free-floating gas clouds. These are the ingredients galaxies need to form new stars, and the filaments act as conveyor belts, delivering them. This steady supply gives filament galaxies access to a richer pantry than those living in sparse regions. As a result, many galaxies along the filaments experience vibrant periods of star formation, almost like factories running around the clock with fresh shipments arriving just in time. The flow of material along the filaments also encourages galaxies to grow more quickly. As gas streams inward, galaxies feed on it, gaining mass and building new generations of stars. Over millions of years, this steady influx can determine whether a galaxy becomes a lightweight system with a modest glow or a hulking giant full of blazing star clusters. Even the shape of a galaxy can be influenced by the web. When gas arrives unevenly from certain directions, galaxies can develop asymmetries, stretching and warping as fresh material pours in. They are not passive structures, they are living constructions, constantly reshaping themselves in response to their surroundings. But the web shapes galaxies in another, more surprising way. It gives their movements direction. Galaxies do not wander randomly. They tend to slide along the filaments, following gravitational gradients like cosmic commuters traveling along predetermined lanes. This motion is slow on human timescales, so slow, in fact, that a single journey might last billions of years. But the path is unmistakable. Over time, galaxies drift toward the intersections of filaments, where the gravitational wells deepen and clusters form. These intersections are the bustling downtowns of the universe, and filaments are the highways feeding into them. A galaxy moving along one of these roads might encounter others traveling the same route. Sometimes these meetings are gentle, like passing someone on the sidewalk. Other times, they are catastrophic, resulting in collisions that dramatically reshape the galaxies involved. These encounters can trigger bursts of star formation, as the disturbance stirs gas into new clumps, igniting fresh stellar generations. In this way, the web orchestrates not only where galaxies travel, but when they get the cosmic equivalent of a growth spurt. Life gets even more interesting for galaxies approaching the densest nodes of the web. As they fall toward these crowded regions, they enter environments teeming with interactions, tidal forces, close passes, and the gravitational tug of multiple nearby galaxies. These conditions can strip gas from a galaxy, distort its shape, or even shut down its star formation altogether. It is as if the galaxy has moved from a peaceful rural landscape into a bustling city center where competition is fierce and resources are quickly consumed. Some galaxies thrive in this environment, merging and growing into massive systems. Others become quiescent husks, their reservoirs depleted by the constant gravitational tussling. Galaxies that remain in quieter stretches of the filaments often retain their gas longer. allowing them to form stars steadily over billions of years. They live calmer, more balanced lives, evolving like small towns, slowly growing over generations. Meanwhile, galaxies in the densest web junctions undergo rapid, dramatic transformations, more like cities expanding in bursts of energy and activity. In this way, the web creates a diversity of galactic life cycles depending on where each galaxy resides. Even the internal chemistry of galaxies is shaped by their position in the web. A galaxy fed by long streams of pristine gas will have a different star-making recipe than one whose gas has been recycled through multiple interactions. Over time, the influx of fresh material can keep a galaxy youthful, full of blue, hot stars. Conversely, galaxies that lose their gas or stop receiving new supplies gradually fade, filled with older, redder stars whose days of explosive energy are behind them. The web determines which galaxies continue thriving and which slowly settle into quiet retirement. One of the most remarkable aspects of this cosmic highway system is that galaxies rarely reverse direction. Once pulled onto a filament, they tend to follow its slope toward denser regions. It is a gravitational one-way road, channeling matter toward the big hubs where the web thickens. Filament galaxies may journey for billions of years, but their trajectory is almost always downhill, pulled by the growing gravitational weight of the clusters ahead. Seen across cosmic time, the web acts like a grand traffic system guiding galaxies from birth to destination. It delivers fuel, regulates growth, sets the stage for interactions, and determines the environments galaxies will eventually call home. Without the web, galaxies would grow in isolation, and the universe would be a scattered landscape of disconnected lights. With it, galaxies become part of a much larger flow, moving and evolving along threads that bind the cosmos together. The cosmic web is not just a structure. It is a dynamic force shaping galaxies at every stage of their lives. It is the universe's silent traffic controller, guiding billions of star cities along invisible roads, ensuring that even across unimaginable distances, nothing evolves entirely alone. If you tell someone that the universe has a skeleton, they might imagine an enormous set of bones floating around in space, perhaps rattling ominously while comets drift past. Thankfully, the reality is less spooky and more poetic. The comparison between the cosmic web and a biological skeleton works not because they look alike, but because they play similar roles. A skeleton gives shape, stability, and organization to an organism. The cosmic web gives those same qualities to the universe, except its bones are made of galaxies, and its joints are clusters so massive that even metaphor struggles to keep up. Yet the analogy holds surprisingly well, as long as we respect the scale difference. A skeleton is a blueprint. The cosmic web is a blueprint writ across billions of light years. Begin with the idea of structure. A skeleton provides the underlying form that everything else builds around. Muscles cling to it, organs nestle within it, and nerves weave through it. Without a skeleton, most animals would collapse into elegant but useless jelly. The cosmic web serves a similar purpose, though its architecture is more subtle. Instead of bones, it uses filaments, enormous strands of matter that define where galaxies gather and how they spread across the universe. These filaments do not resemble ribs or femurs, but they do provide a framework. Galaxies arrange themselves along these threads, finding their place the same way organs settle into their skeletal containers. Then there is the idea of connection. A biological skeleton links distant parts of the body into a coherent whole. Your wrist depends on your elbow, which depends on your shoulder, which depends on your spine. Each piece interacts with others through joints, forming a network of influence. The cosmic web's filaments do the same for galaxies. They connect clusters across unimaginable distances, creating a continuous flow of matter and motion. They are the universe's way of keeping everything linked, even when the distances are so great that light takes eons just across from one region to another. The analogy becomes even more compelling when we consider growth. A skeleton grows with its organism, expanding, lengthening, and strengthening as the creature matures. The cosmic web, too, has grown over time. In the early universe, its filaments were faint, nearly invisible hints of structure. As matter accumulated, these threads thickened, stretching farther and shaping larger formations. Just as a child's bones slowly transform into the sturdy structure of an adult, the cosmic web evolved from a delicate pattern into the colossal framework we observe today. It did so not through biological instruction, but through the steady influence of gravity acting across cosmic time. Another parallel is guidance. A skeleton helps determine how a body moves. Your legs are shaped to walk, run, jump, and occasionally trip in public. The cosmic web guides the movement of galaxies in much the same quiet manner. The filaments channel galaxies along gravitational slopes, directing their journeys toward denser intersections. These cosmic joints form clusters where galaxies gather in staggering numbers. Instead of cartilage and ligaments connecting bones, these joints are held together by gravity and the pull of unseen matter. Movement in both systems follows paths sculpted by the underlying structure. There is also the concept of support. A skeleton holds weight, distributes pressure, and prevents collapse. Without one, even the strongest muscles cannot provide stability. The cosmic web supports the cosmos by collecting and organizing matter so that galaxies have a place to form. Without this network, matter would be spread too thinly for complexity to emerge. The universe might have remained a diffuse haze instead of turning into a richly structured landscape. In both cases, body and universe, the framework is essential for complexity to take shape. Of course, no analogy is perfect, and this one needs boundaries to avoid drifting into the absurd. A skeleton is made of living tissue. The cosmic web is built from clusters of galaxies and invisible mass. A skeleton has a definite shape. The cosmic web's shape is ever-changing, influenced by expansion and shifting matter. Bones cannot rearrange themselves at will, but the cosmic web can subtly shift as matter flows along its filaments. And while an organism has a single skeleton, the universe's skeleton is a sprawling network with no central axis, no left or right, no top or bottom, just a vast web stretching in every direction. Yet these differences do not diminish the usefulness of the analogy. Instead, they highlight its strength. By comparing the cosmic web to a skeleton, we capture something essential, the idea of an invisible structure silently shaping everything around it. Most of us will never see a galaxy cluster with our own eyes, but we all understand the role of bones. The analogy builds a bridge between the intimate and the immense, helping us perceive the universe in a way that feels tactile, almost familiar. The comparison also offers emotional resonance. A skeleton feels elemental, foundational. Knowing that the universe has its own version of that foundation gives the cosmos a sense of coherence. It transforms an otherwise overwhelming expanse of stars and darkness into something unified, something with form and intention. It whispers that the universe is not just an explosion of matter flung in all directions, but a system with deeper organization, shaped by forces we are only beginning to understand. In the end, the cosmic web is not a skeleton in the literal sense. It does not creak, crack, or complain about the weather, but it does bind the universe together, give it shape, and allow galaxies to grow and move with purpose. It is a skeleton in spirit, a cosmic echo of the same architectural principles that govern living creatures. And through this analogy, we glimpse the universe as something both astonishingly vast and strangely relatable, a giant with bones made of galaxies, holding its structure across the darkness. Imagine setting out on a journey so ambitious that ordinary travel becomes a warm-up exercise. No planets hopping, no star-to-star doodling, just pure intergalactic wandering. You drift away from familiar starlight until your home galaxy shrinks to a faint, spinning memory in the distance. Out here between the islands of cosmic structure, you begin to notice something remarkable. The universe is not an endless drape of evenly scattered galaxies. Instead, it is marked by grand, sweeping pathways, filaments that serve as the universe's natural highways. If you were an intergalactic traveler, these filaments would be your road signs, your compass bearings, your glowing landmarks in the deep dark. From your viewpoint, each filament would not appear as a single straight line. Instead, it would stretch like a nebulous, sprawling corridor, glowing faintly with the combined shimmer of countless galaxies. The galaxies would seem like lanterns pinned along an invisible thread, flickering softly across distances so massive that even your advanced instruments struggle to register the full extent. Traveling alongside a filament would feel like flying through a canyon made of starlight. On one side, galaxies cluster in luminous chains. On the other, they curve away into the shadows, forming gentle arcs that hint at gravitational currents far too subtle for the naked eye. As you glide closer, you would sense the influence of these invisible currents. The path ahead is not random. The filament guides you, not through physical rails or restrictions, but through gravity's soft persuasion. You do not drift aimlessly. You follow the slow pull that shapes the motion of galaxies themselves. Even without a map, you can tell which direction the cosmic current flows, toward the thicker regions where galaxies grow more crowded and bright. If you could listen to gravity, it would be humming these directions like a low, steady note, never forceful but impossible to ignore. Your navigation system would quickly learn that the filaments do more than guide, they divide. On one side, you peer into the immense openness of a void, a realm so empty that the nearest beacon of light sits unimaginably far away. It feels like staring over the edge of a cliff carved from nothingness. The void gives no assistance, no sense of direction. It is an ocean of darkness with no landmarks to read. But pivot back toward the filament, and the cosmos regains its structure. The galaxies brighten, the geometry sharpens, and the path becomes recognizable again. For a traveler, the filament becomes an anchor, a trail of lights marking safe passage through a universe with overwhelmingly vast stretches of emptiness. Moving along one of these cosmic corridors, you would begin to notice variations in the scenery. Some stretches feel crowded, bustling almost, filled with swirling galaxies that glimmer like cosmic cities. Others grow sparse, thinning into delicate wisps, where only a few galaxies gleam like solitary lighthouses, marking the boundaries of the road. These changes are clues to the underlying mass distribution. Regions where matter is plentiful form thicker lanes, while thinner ones have fewer travelers to accompany you. And eventually, as you glide farther along the filament, you encounter one of the profound intersections of the cosmic web. Ahead, the galaxies grow denser, clustering into brilliant knots where multiple filaments converge. From afar, this region looks like a shimmering crossroads in the dark, a grand hub at the center of several glowing corridors. For an intergalactic traveler, such an intersection is a navigational jackpot. It is the cosmic equivalent of finding a major interchange where every direction leads toward new star systems, new clusters, new arms of the web waiting to be explored. If you drift into this hub, you can almost feel the gravitational tension under your craft. The pull is stronger, more complex, tugging you from multiple directions as the combined mass of the region asserts itself. It feels like gliding through the heart of a cosmic metropolis, surrounded by an overwhelming concentration of light, structure, and celestial traffic. Each nearby galaxy stands out like a landmark, a bright spiral here, an elliptical giant there, a chaotic, clumpy system flickering in the cosmic fog. If you were keeping a travel log, this is where you would write, "Arrived at Grand Junction, spectacular, crowded, slightly overwhelming, must visit again." The filaments do more than guide you physically. They offer a kind of cosmic storytelling. Their curvature hints at ancient flows of matter, at eons of gravitational shaping that began long before the galaxies you see were even born. If you trace a filament long enough, you begin to feel the history written into its shape. Some parts are smooth, as though carved gently by steady cosmic currents. Others display fractures or bends, the gravitational signatures of long-past mergers and collisions between galaxy clusters. The web becomes not just a map, but a record of the universe's evolution etched across space. From your vantage point, the web also reveals something profound. Everything is connected. No filament is isolated. No cluster is an island. Every glowing strand leads to another, forming a grand, continuous architecture that spans the cosmos. As a traveler, you would come to appreciate the unity of it. No matter how far you journey, no matter how remote a region appears, some faint thread always stretches onward, guiding you toward the next luminous gathering. If you were to leave a filament, perhaps out of curiosity, or the thrill of exploring the unknown, you would quickly feel the difference. Drift into a void, and the universe becomes a featureless sea. The reference points vanish, the gravitational whispers fade, your sense of direction dissolves. It is a sobering reminder. Travel without structure is travel without meaning. You would soon turn back, searching again for the soft glow of the filament, grateful for its quiet guidance. In this speculative journey, the cosmic web becomes more than a scientific concept. It becomes a traveler's lifeline, a network of luminous pathways stretching across unimaginable distances. To wander these threads is to explore the universe the way galaxies themselves do, following the ancient routes charted by gravity and time. And in doing so, you cannot help but feel that the web is not just a structure, but a cosmic invitation, one that promises endless destinations, endless discoveries, and endless wonder woven into every glowing strand. Imagine waking up in a universe where the grand cosmic web simply never happened. No filaments stretching across billions of light years, no galaxy clusters gathering like cosmic block parties, no majestic intersections where countless galaxies meet. Instead, picture a cosmos that shrugged at the idea of structure and wandered off to do something else. It is a universe where matter never got organized, where everything is scattered in a kind of cosmic confetti storm that never settles. If our universe with a web is a symphony orchestra playing a slow, elegant crescendo, then this alternate version is a crowd of people shaking maracas with no rhythm, no conductor, and no idea what the song was supposed to be. Let us start with the basics. In our universe, tiny variations in density grew into the grand scaffolding of filaments and nodes. In a universe without that initial unevenness, one where matter was spread out almost perfectly evenly, gravity would have nothing to amplify. It would try its best, of course. Gravity always tries. It would nudge matter, tug on it gently, politely ask it to clump together. But if all the matter is too evenly distributed, the nudges never build into anything meaningful. The universe becomes a quiet, uneventful expanse where gravity keeps clearing its throat, waiting for something exciting to happen, and the cosmos refuses to deliver. In such a smooth universe, galaxies would struggle to form at all. Without denser pockets where matter can gather, the process of building stars becomes painfully inefficient. Gas would remain thinly spread, drifting like a faint mist across space. Here and there, tiny regions might manage to collapse enough to produce a star or two, but large structures, Spiral galaxies, glittering ellipticals, massive clusters simply would not appear. The night sky, for any hypothetical observer, would be a lonely place. Instead of a rich canvas filled with islands of starlight, you would see the occasional solitary spark floating in darkness, like a tiny campfire too far away to warm anything. The emptiness would feel different too. In our universe, voids exist because filaments hoard the matter, leaving behind pockets of nothingness. But in a universe with no cosmic web, the entire cosmos is essentially one giant void. Not a dramatic chasm between structures, but a vast, uniform sea where almost nothing stands out. If you traveled for billions of light years, you would encounter the same lonely scenery over and over: wisps of gas, a few wandering stars, maybe a small cluster struggling to hold itself together. It would be like living in a neighborhood where every house is miles apart and every resident prefers not to talk. The lack of structure would make cosmic evolution painfully slow. Stars rely on dense clouds of gas to trigger their formation, but without filaments funneling and concentrating that gas, those clouds rarely get dense enough. Even the stars that do manage to form would live in isolation. No bustling galactic communities, no swirling arms, no interactions that reshape galaxies and trigger new generations of stars. Star formation would be a timid trickle instead of the energetic cycle we see today. The universe would grow old gracefully, too gracefully, without the fireworks of merging galaxies or starburst events lighting up the dark. Planets would have a hard time appearing too. They form from debris that gathers around young stars. But if only a sparse number of stars ever form, then planets become rare treasures. And without large galaxies stirring up gas, recycling material, and forging heavy elements in repeated cycles of creation and destruction, many of the ingredients for complex chemistry simply would not exist. The universe might remain stuck with the simplest ingredients for eons, unable to cook up the richer elements needed for planets, oceans, and life. Even the behavior of light would change. In our cosmic web-supported universe, light travels past galaxy clusters that bend and stretch it through gravitational influence, creating beautiful distortions that help scientists map the underlying structure. Without massive clusters or large-scale variations in density, those distortions vanish. Light would move across the universe almost entirely undisturbed, like a beam sliding through an empty hall. For astronomers, it would be a kind of observational boredom. The cosmos would offer few clues about its shape, because it would not have a shape to speak of, just a smooth, uneventful backdrop. Perhaps the strangest part of this structureless universe is how emotionally different it would feel. Our universe is filled with drama, galaxies colliding, stars exploding, clusters forming in dazzling displays of light and force. The cosmic web pulls matter into vibrant complexity, but a universe without that web would be eerily quiet, like a stage where the actors never arrived. The cosmic story would have almost no plot, just endless space punctuated by occasional isolated acts of star formation that never blossom into anything larger. And what about the grand, sweeping architecture of the night sky, the constellations, the glowing band of our galaxy, the dense star fields that make you feel like the universe is teeming with possibilities. All of that vanishes. Without galaxies clustering into shapes, without stars forming in huge numbers, the sky becomes sparse. A lonely handful of stars might adorn the darkness, but not enough to inspire myth, wonder, or the feeling that you are part of something larger. The universe would feel like a house with only one or two lights on, barely enough to illuminate the hallway. In this alternate reality, the universe does not fail. It just never organizes itself. It is a cosmic procrastinator that skipped the day gravity-held orientation. Without the cosmic web, the universe never builds the grand skeleton that supports complexity. It is existence without architecture, a cosmos that never bothered to discover its own potential. And yet, by imagining it, we appreciate our own universe all the more. The cosmic web is not just a structure. It is the reason the universe grew interesting. It is the silent architect behind galaxies, stars, planets, and everything that gives the cosmos its breathtaking richness. Without it, the universe would be a smooth, dark, and quiet place. With it, we get a cosmic masterpiece woven across the sky. If you step back far enough, far beyond solar systems, beyond galaxies, beyond even clusters of galaxies, you begin to see the universe not as a jumble of isolated islands, but as an intricate, interconnected masterpiece. It is almost poetic how the cosmos, born from a moment of pure, unfiltered chaos, somehow organized itself into a structure so vast and graceful that it puts every human attempt at architecture to shame. The cosmic web is that structure. It is the universe's great achievement, the grand reminder that order can bloom from noise, and that the cosmos is far more sculpted than it first appears. This story began with turbulence, a young universe expanding rapidly, particles bumping into each other like a crowd trying to exit a concert all at once. Nothing in those moments suggested that anything structured would emerge. The early cosmos was a swirling fog of potential, bright and hot and entirely uncommitted to the notion of organization. And yet, little by little, gravity started weaving faint patterns into the glow. The tiniest differences in density, so small they might as well have been whispers, became the seeds of everything to come. Those whispers grew into threads. The threads grew into filaments. The filaments linked into a sprawling network that now stretches across the entire observable universe. It is easy to admire the cosmic web for its scale alone. After all, it spans billions of light years and ties together everything from humble galaxies to enormous superclusters. But what makes the web truly astonishing is its quiet patience. It did not appear overnight. It took billions of years of slow, deliberate shaping, matter drifting, merging, collapsing, and rearranging itself along invisible currents. The web is not something the universe built quickly. It is something the universe grew into, like a creature slowly discovering its own skeletal shape. When we look at the cosmic web today, we see something that feels almost alive. Filaments stretch like tendons, nodes gather like joints, voids expand like vast lungs inhaling the dark. The structure feels organic, not because it mimics any familiar biology, but because it embodies the same principles: connection, support, balance, and evolution. The cosmic web is the universe learning to stand on its own, discovering a framework that lets stars ignite, galaxies flourish, and complexity bloom in places that were once nothing more than scattered particles, drifting aimlessly through expanding space. There is something deeply moving about the idea that the universe did not settle for randomness. It could have remained a uniform haze, silent and uneventful, without ever forming galaxies, planets, or the possibility of beings who could look up at the night sky and wonder. Instead, it allowed subtle differences to grow into grand architecture. From the faintest variations in ancient light came a scaffold strong enough to cradle enormous structures. And from those structures emerged everything we know: worlds, elements, oceans, and eventually minds capable of asking how it all came to be. When we chart the cosmic web, we are not just mapping the positions of galaxies, we are tracing the universe's long path toward structure. We are following the way gravity nudged matter into patterns, the way dark matter shaped unseen foundations, the way filaments extended into extraordinary bridges between realms of light. In doing so, we uncover a message the universe has been writing for billions of years. Complexity does not need perfect order to appear. It only needs time, gentle guiding forces, and the willingness to let imperfections grow into pathways. Perhaps what makes the cosmic web most compelling is how it reframes the idea of chaos. Chaos is often imagined as destructive, unruly, the opposite of design. Yet the universe began with chaos, and instead of eliminating it, the cosmic web arose by embracing it. The earliest fluctuations were not flaws, they were features, tiny invitations for gravity to begin its sculpting. Without those initial irregularities, the universe might never have developed any structure at all. The cosmic web is proof that chaos does not have to be corrected. It can be the beginning of something extraordinary. Reflecting on this grand structure also reminds us of our place within it. The Milky Way, our vast and dazzling home, is just one thread in a tapestry so large that its edges remain beyond visibility. Our galaxy drifts along a filament, following ancient currents, surrounded by countless other galaxies moving along their own gravitational paths. We are inhabitants of a structure we cannot perceive directly, but can understand through the light that reaches us across unimaginable distances. The cosmic web is the quiet architecture beneath our cosmic neighborhood, supporting our very existence without ever announcing itself. And so, as we bring this journey to a close, the idea of the cosmic web becomes more than a scientific concept. It becomes a metaphor for the universe itself, a testament to how structure emerges from disorder, how beauty arises from simplicity, and how the cosmos grew a skeleton, not because it needed one, but because it could. The web is the universe's whispered reminder that even the wildest beginnings can evolve into something elegant. In the end, the cosmic web may be the universe's way of showing that chaos is not the enemy of structure. It is the raw material from which structure is shaped. And across billions of years, the universe sculpted that chaos into a backbone, a luminous, sprawling skeleton that holds the cosmos together and invites us to look deeper, dream bigger, and marvel at the architecture of existence itself.